Thank you for joining us tonight for our Caltech Astronomy Stargazing lecture. We've got a great evening planned, and the weather looks really positive for clear weather for our telescopes being set up right now. So a few announcements, and then we'll get started with the talk, which will last about 30 minutes on the history of the universe with radio astronomy, and then we'll have a brief Q&A with our speaker, and then the remainder of the night we'll have a Q&A panel set up in this room consisting of myself, our speaker, and two other members of the department to answer your general questions about astronomy, space science, physics, as well as content from the presentation that you're about to hear. And at the same time, we'll have telescopes set up outside. If you follow the signs, go out the door that you came in, go around the building, and you can follow signs about a couple 100 feet to the athletic fields right behind me. And right now, because it's clear, there's the planet parade going on. So there's a lot of planetary objects to look at, as well as deep sky images. or deep sky objects. So I think what they're setting up are to look at the first quarter moon, which is always a beautiful target, to look at Jupiter and perhaps Mars, and then to look at a deeper sky object like the Orion Nebula or Bode's Galaxy or M82, something like that. So it'll be great. So definitely check that out, and we'll continue to do this until about 9:45 or so. And whenever you want to leave, you're free to leave. So other announcements. Just a couple of weeks ago, we had the Death Valley Dark Sky Festival. Raise your hand if you were able to attend. I know some of the people came. Okay, so nobody came, but we were there, and it was great. So we brought almost 24 students up and organized a bunch of activities, some presentations, some science demonstrations, set up telescopes and the like, and it was great. It happens annually in February or so, and Death Valley is a pleasant place to be. And it's open to the public. I think there were 7,000 people who showed up this year. So it's really cool, and we'll be helping out again next year. Similarly, later in the year, there are other national parks that have dark sky festivals. Sequoia, which is only 4 or 5 hours drive from here, also has one, but that takes place in September. It'd be far too cold right now to go visit Sequoia. And we may be assisting with the Grand Canyon and Great Basin National Parks as well, but I'll keep you guys aware of our plans. What else is going on? These events take place once a month. Our next one of these will be Friday, April 4th or April 5th. I forget which day it is, but it's the first Friday of April that we'll be hosting. And I don't yet have a speaker, but stay tuned, and I'll put it out on our social media and our mailing list and our website and so on and so forth. In addition to these events, we have Astronomy on Tap that takes place once a month at a bar in Old Town Pasadena, the Doghouse. It's an outdoor beer garden area, and it's similar to this, but it's a little less formal. It's in a bar or restaurant. It's open to all ages, and that consists of 2 15 to 20-minute presentations given by local scientists, both here at Caltech, as well as Carnegie Observatories, NASA Jet Propulsion Laboratory, UCLA, who come and give presentations. There's astronomy-themed pub trivia. There's telescopes at that as well, and live music. So it tends to... Don't worry, it's not you. I got that beep earlier, so you can't control the beeps when they start beeping. So the next one of those will be 2 weeks from this coming Monday. It's always on a Monday night because the bar won't let us do it on a Friday night. And the topic, and one of the presenters, I think both of the presentations will be on cosmology, kind of the study of the universe, and one of the presenters will be a professor here, Jamie Bach, who notably is the principal investigator, kind of the head scientist who's launching a NASA mission tomorrow. This is a mission that you may have seen in the news. It's called NASA SPHEREx, and it's going to be a space telescope that's specifically looking at hundreds of thousands of galaxies to try and identify tracers of larger cosmological structure, but also tell us something about the early universe when the universe inflated very, very rapidly. It's also going to study ices. Anyway, he's going to give the Astronomy on Tap talk, so I encourage you guys to come. And if you're interested in seeing the launch is taking place tomorrow night at just after 7 p.m. from Vandenberg Air Force Base, which is just a couple hours drive from here. You can't go to the base unless you have like military clearance, but you can go outside the base and watch the launch if you want to. And I know a number of people from Caltech are going up because this is a major Caltech mission. But even if you don't go up, it may be possible. Perhaps you've seen, living here in Los Angeles, after sunset, you can sometimes see launch plumes going up. So it may be possible to see, if you look up to the northwest around 7:15, you may see one of these launch plumes from this rocket that's carrying this spacecraft into space. So that's quite exciting. I think those are all of my announcements. So we'll get started with our speaker. So our speaker grew up in the Pacific Northwest in Portland, and did her undergraduate studies at Macalester College in Minnesota and studied physics and mathematics before she pursued her PhD at University of Washington back in the Pacific Northwest, finishing there just a couple of years ago and getting her PhD in physics. And then she started as a postdoctoral researcher here at Caltech in 2021 and has been here ever since, and now has one of these kind of highly categorized prize postdocs called the National Science Foundation Postdoctoral Fellowship. And she's doing some really incredible work on radio astronomy, much like she's going to talk about now, but in particular looking at the study of cool hydrogen throughout the evolution of the universe and what it can tell us about the entirety of the universe and its evolution. So please welcome our speaker, Dr. Ruby Byrne.
Thank you so much for that introduction, Cameron. Yeah, let's get started. Uncovering the history of the universe with radio astronomy. So in this talk, this is designed to be accessible to folks who do not have a lot of background in science or anything like that. And I'm hoping to answer these three questions. So first of all, what is observational cosmology? Second, what is radio astronomy? And those are just going to keep happening this whole talk, so don't even feel bad about it. It's totally good. And third, kind of bringing those two questions together, how can we use radio astronomy to learn about the early universe? So starting off, what is observational cosmology? Well, just looking at the two parts of this term, cosmology refers to the science of the origin and development of the universe. Observational specifies that we're using measurements from scientific instruments such as telescopes to do cosmology. So we're not just sitting around doing equations, trying to understand theoretically what's going on in the universe. We're actually making measurements of the universe. And we do this by measuring light from very distant objects. So if we think about objects that produce light that we can see on Earth, that light moves very quickly, but it does have a finite speed. This means that it takes light from our sun 8 minutes to reach us. If we go further out in space, Proxima Centauri, our closest star, it takes light 4 years to reach us. So that means that when we look out at Proxima Centauri, we're not seeing the light that was emitted in 2025. We're seeing the light that was emitted around the time that I was starting my postdoc in 2021. If we look at even more distant objects, such as the center of our Milky Way galaxy, where the Milky Way is really our cosmic neighborhood, it takes the light 26,500 years to reach us. So we see that these numbers get bigger very quickly as we move out in space. Andromeda galaxy is 2.5 million light years away. As we go to even more distant objects, such as the most distant galaxies detected by JWST, it might have taken that light millions or even billions of years to reach us, with the most distant objects we can see having light travel times of 13 billion years. So this is a fun fact. You might hear people say that some of the stars, the pinpricks of light we see out in the sky when we look out, no longer exist, that they've since died. But it's actually a lot more than a fun fact. This is a tool that observational cosmologists use, because it means that when we look at these very distant objects, we're getting a snapshot from the early universe. We're getting essentially historical artifacts of what the universe looked like a long time ago. And so we can use these to piece together the history of the universe. And I'd like to take a bit of a historical perspective when I'm talking about what observational cosmology is, and talk about the key observations that have motivated our standard model of the universe. So the first of these is the discovery that the universe is expanding. And this was really enabled by work done 100 years ago in the 1920s. And this was led by Henrietta Swan Leavitt, She worked as, her job title was computer at Harvard University, and it was a role that a lot of women who were involved in astronomy at the time held. The idea is that these women were doing the computations that supported astronomical discovery. She obviously went far beyond doing rote computations and really kicked off the field of observational cosmology. And what she discovered is that we can use these variable stars called Cepheids to very accurately measure distances in the universe. Edwin Hubble, here in Pasadena, actually applied this method of using Cepheids to measure the distance to the Andromeda galaxy. So this is the Andromeda galaxy shown here, and then in the lower right, that's actually the image that he made using the 100-inch telescope at Carnegie observatories. You can see that he wrote VAR exclamation point there, and that is his discovery of a Cepheid within Andromeda. Using that discovery of the Cepheid, he then found that Andromeda was much more distant than some people had thought. So at this time, it was hypothesized that the Milky Way was the full extent of the universe. And what he found in this discovery is that Andromeda actually lives outside of the Milky Way. It's very distant, and the universe was much bigger than previously thought. But he didn't stop there. So then he and kind of simultaneously this other astronomer named Georges Lemaitre, who is a Belgian Jesuit priest, interestingly, they applied this method to much more distant galaxies. And this is a sample of those galaxies. This is from a 1929 paper by Hubble, looking at the distance to many galaxies with light travel times of up to 6.5 million years. And then on the vertical axis here is their velocity. And you can see that there's a relationship where the more distant galaxies are moving more quickly than the closer in galaxies. So what is this telling us? I think it's helpful to draw a cartoon here. So if we imagine ourselves standing on Earth looking out at the universe around us, we see all of the galaxies around us moving away. And the more close-in galaxies are moving away more slowly than the more distant galaxies. And this is telling us that the universe is expanding. And I want to emphasize showing this cartoon here that this is not specific to us being on Earth. If we were to be anywhere else in the universe, we would see much the same thing. And so the universe is really expanding from every point in the universe. Pretty wild to think about. Anyway, a follow-up discovery is that the universe's expansion is actually accelerating. And this is attributed to these three scientists. They made this discovery in the 1990s and received the 2011 Nobel Prize for it. And they kind of just replicated the work that Hubble and others were doing. So this is the exact same kind of plot here. Along the horizontal axis, you have distance to galaxies, but now instead of millions of years in light travel time, they went up to 7.8 billion years in light travel time. At these distances, you can no longer use Cepheids, so they use supernovae to measure these distances. And then on the vertical axis, once again, you have the velocities or the speeds of those galaxies. And you can see that there's a deviation from a line here. And that deviation is indicating that the universe is not only expanding, but that that expansion is accelerating. Another key discovery in observational cosmology is that not all matter is visible. So this was first hypothesized by Fritz Zwicky in the 1930s and later confirmed by Vera Rubin. This is an image of the Andromeda galaxy, once again, where all of these points are stars in Andromeda. And then on this side, you see the distance from the center of Andromeda to those stars and their rotational velocities on the vertical axis. And what Vera Rubin found is that there's a deviation from the expectation for how fast this thing rotates. And essentially, you cannot explain the rotation of galaxies based on the visible stars we see. So there has to be something else going on. And we call this thing dark matter. And it's called dark matter basically because our telescopes can't pick it up, and also because it's mysterious. We still don't know what it is. And so it's one of the great mysteries in modern cosmology. And finally, another key discovery in observational cosmology, probably the most important to date, is the discovery of the cosmic microwave background, or CMB. And this was the first really observational evidence we had that the universe was once dense and hot. This was made in 1964. Using this telescope here. This is the Holmdel Horn antenna in New Jersey. And the discovery was made by Arno Penzias and Robert Wilson, and they received the 1978 Nobel Prize for it. What they saw is, pointing this telescope in any direction on the sky, there was a glow that couldn't be explained by any other astrophysical phenomenon. And this glow was nearly uniform across the entire sky. It turns out that this is light with a light travel time of 13.8 billion years, and it's actually the most distant light we can see in the universe. Essentially, the only way that there could be this uniform glow from every direction on the sky is if the universe was once very small, very dense, and very hot. And this tells us that the universe started off with something like a Big Bang. Now, that emission, that light from every direction on the sky is very uniform, but there are some variations. And so follow-up experiments have measured this. This is the Planck satellite, which gives us some of the best measurements to date of the variations in the cosmic microwave background that look like this. And they're really quite small. They're 1 part in 100,000. These variations look kind of random, but they actually encode a lot of interesting information about the early universe. They tell us things about dark matter in the very early universe, about how old the universe is, about how fast it's expanded, things like that. So together, it's really been, a wonderful century of observational cosmology. We've learned a lot about the universe, and these discoveries have led to our current understanding of cosmology. That's kind of summed up in this diagram here. And this is really a cartoon of the universe where you can think of it as a timeline. So time is increasing to the right. We expect that the Big Bang started off the universe, and this is really given by evidence of the CMB. The CMB was emitted 370,000 years after the Big Bang. So what happened here is the universe was once very, very dense and hot, and it expanded rapidly. It ultimately expanded sufficiently so that it cooled off enough to become transparent for the first time. It stopped glowing. That's when we get the CMB. Following the CMB, the universe entered what's called the Dark Ages. And they're called the Dark Ages because there were no bright objects. There were no stars and galaxies throughout the universe. Essentially, all there was gas as well as dark matter. Not a very exciting time, but an exciting process was happening behind the scenes. That gas and dark matter was spread out throughout the universe fairly uniformly, but it did have some overdensity, some regions where more of that gas and dark matter were clumped together. Now, gravity was having an effect on those clumpy regions, and it was cramming them together, pushing them together more and more. Eventually, they became dense enough that they ignited. And this forms the first stars, what we call the cosmic dawn, when the universe lit up again. And this occurred about 400 million years after the Big Bang. So you can see that it's really hundreds of millions of years of dark ages before anything more exciting happened. Next, these galaxies interacted with the surrounding universe and heated it. And that brings us into further galaxy, star, and planet evolution. So you get more sophisticated galaxies, you get supernova explosions that are going to synthesize new elements that previously didn't exist in the universe. You also get all sorts of planets surrounding these stars. And we get accelerating expansion of the universe, bringing us to the present day, which is 13.8 billion years after the Big Bang. So I can show you this cartoon here, and I can say we figured it out, in the last 100 years of observations. We're good. We understand what happened. And I can talk all day about what we know. But I'm more interested in what we don't know. So what are the gaps in this? And in particular, the gaps are these things: the dark ages, the cosmic dawn, and the heating of the universe by those first stars and galaxies. We don't have any direct observational evidence of those. And so there's a lot of question marks about what actually was going on. So questions that I aim to answer in my research are things like, when did the first stars turn on? What was the timing of the cosmic dawn? What is the universe's expansion history? What are the properties of dark matter? What is actually going on with this mysterious substance called dark matter? What are the characteristics of the early galaxy populations? Were these first populations of galaxies very massive, very large, or were they smaller? How abundant are black holes throughout history? We know that there's quite a few black holes in the modern universe. Were there more in the early universe? And how efficiently did early stars heat the universe? And I'm doing this with this telescope shown here. This is a long wavelength array at the Owens Valley Radio Observatory, or the OVRO LWA for short. So the Owens Valley Radio Observatory is located about a 4 hours drive away in Bishop, California. It's a really beautiful part of the state if you haven't been out there. If you do go out there, I highly recommend that you stop by the observatory. We have a ton of radio telescopes there doing a lot of incredible science. My favorite is this one here. So it's these tent-shaped antennas that we're using to study the early universe. So I'd like to talk more about this, but first of all, some background on what radio astronomy is. So light comes in different varieties or colors, and these correspond to different wavelengths. So when our eyes pick up purple light, that has a very short wavelength, and red light has a very long wavelength. So these are of light that our eyes can see, but they're just a small class of the different types of light that exist. We have wavelengths of light that are shorter than our eyes can pick up. These correspond to UV rays, X-rays, and gamma rays. We also have light that has too long of a wavelength for our eyes to pick up, corresponding to infrared and radio waves. I'm a radio astronomer, so I work out here. I work with very long wavelengths of light. And in particular, the OVRO LWA looks at light with wavelengths around here. So this is roughly corresponding to the FM band. So it's the same kind of light that operates the radio in your car. This is light with wavelengths of 3.5 to 25 meters or 11.5 to 82 feet. So it's really huge wavelengths. So this little stick figure here is an average sized human, I think 5'7". And these are the kinds of wavelengths compared to that average sized human that our telescope is picking up. So really quite long. We can do this measurement with this telescope because the atmosphere is actually allows these long wavelengths of light through. So this here is showing all the different wavelengths of light along the horizontal axis, and along the vertical axis is the atmospheric opacity. So this is telling us whether that light is allowed through our atmosphere. You can see that visible light is, which is great. This is why you can see the sun. Shorter wavelengths of light are not allowed through, and this might be a little inconvenient for certain astronomers. It's actually very convenient for cellular life because these short wavelengths of light carry a lot of energy and would basically blast apart our DNA if they all made it through. You also see that radio waves can make it to Earth, and the OVRO LWA is unique in that it operates at the very longest wavelengths that we can measure from Earth. So we're really pushing the limits of where we can do astronomy without having to go to space. If we want to measure anything out here, the very longest wavelengths, we would have to go to space, and there are proposals to build a telescope on the moon to do just that. Now, I keep emphasizing these are very long wavelengths of light. That means our telescopes have to be absolutely enormous. And to put this in perspective, this is an optical telescope. An optical telescope means that it measures visible light that we can see with our eyes. It has a wavelength of about 500 nanometers. This particular telescope is one that will be set up after this talk, so if you want to go check it out, please do. It's a really great telescope. You can see a lot with it. And it has a diameter of 11.4 centimeters. If we wanted to build a radio telescope like the one that I use with equivalent resolution to this telescope, so able to see the same kind of stuff, it would have to be this big. It would have a diameter of 800 kilometers. So yeah, they're absolutely enormous. And we don't have an 800 kilometer telescope, but we do have a pretty big one. It's 2.4 kilometers. And the way we do that is by using a lot of different telescopes together. So we actually have 352 of these antennas or little mini telescopes that work together like one big telescope. And it's shown on the right here. This is just, a map of where all of those antennas are. The orange ones were the first ones we built, and we've just been expanding out the array since then. So next we built all of the blue ones and then all of the green ones, bringing the total up to 352. And this is really a great telescope for a lot of reasons. This is just an example of the images that it makes. It sees the entire sky above the horizon in just a few seconds of data. So this here is the entire sky at these very long wavelengths of light with 10 seconds of data, and then zooming in with 10 minutes of data, you can see this beautiful supernova remnant. Now, we're making these beautiful images. We're doing a lot of science with this telescope. There's so many different things we can see with it. I'm particularly interested in the cosmology, so looking at the very distant light that can tell us about the early universe. So this brings us to the last question of this talk. How can we use radio astronomy to learn about the early universe? So once again, this is going back to these kind of mysterious eras in the universe's history, the dark ages, the cosmic dawn, and the heating of the universe by early stars and galaxies. This is what we want direct observational evidence of using this telescope. And the key to doing this is our friend hydrogen. So this is the periodic table. It's a chart of all of the elements we have. And hydrogen has a very special place on the periodic table in the upper left. And that is because it's the simplest element. It consists of just two particles, a proton and an electron. And the reason I love hydrogen so much and I'm so interested in it is because it produces light at a very specific wavelength of 21 centimeters. So this is right in the radio class of light. And the hydrogen signal from the early universe varies depending on what is going on with hydrogen. It depends on the temperature of that hydrogen. It depends on its density, so we get more of this light when we have more hydrogen in one place. And it also depends on its ionization state. And ionization state just means whether that proton and electron are bound together or whether they're separate. And all of these things tell us about the universe's structure and evolution. So this image here was created as a simulation of what this signal looks like in the early universe. You see these bright bubbles and dark around them. And this is really telling us about how early stars and galaxies are interacting with the surrounding gas. So we have regions of really bright signal and regions of no signal. And this is exactly what we want to measure. If we're able to measure this, we're able to test these simulations, know if this person got it right with this or if there's some other physics going on. And we really also don't know when this happened in the universe's history. Now, this light from hydrogen is emitted with that wavelength of 21 centimeters, but we don't see it at 21 centimeters. This is light that was emitted billions of years ago, and a lot has happened in a billion years. One of the things that has happened is the universe has expanded, and that has stretched out that wavelength of light. So the light that we actually measure has a much longer wavelength than 21 centimeters. And this is actually exactly where we measure with the OVRO LWA. This is also a useful tool that we have because when we measure a specific wavelength of light, we can determine the distance to the hydrogen that emitted it. When we measure shorter wavelengths, we know that that hydrogen was nearer to us, and longer wavelengths indicate very distant hydrogen. And so what we do is we not only measure where hydrogen lives across the sky, but we measure the distance. We get 3D maps of the entire universe. And as we step through cosmic time, this corresponds to different periods in the universe's history. So we're actually mapping out the whole thing in hydrogen. Now, this is a very faint signal that we're looking for. We're hoping to see this, but there's a lot of other stuff we see. We see intervening galaxies. We see our own galaxy. And these together are 1,000 times brighter than what we're looking for. We also have distortion from our atmosphere. And all of this is backlit by that CMB emission, by the cosmic microwave background. So we're trying to pick out just this layer, but all of these things are smushed together. So this is really a challenging data processing problem. We need to filter out all of these other sources of contamination so that we can see our signal. To make matters even worse, us humans use radio waves for other stuff. So we have a lot of radio frequency interference, or RFI, created by our telecommunication devices that also contaminates the signal that we need to filter out. So where are we now? This is really exciting science that we can potentially do, and we're still on the path to achieving it. We've not yet measured the signal. What we have achieved is upper limits on the signal brightness. So we essentially know how sensitive our instruments are. We know we haven't seen anything yet. And so we can rule out any sorts of simulations or any predictions that would produce a signal brighter than that. And we're progressively improving our sensitivity, beating down where we know the signal is not, and ultimately we hope to actually measure it. And we're making a ton of progress improving the overall LWA and our analyses. So we've upgraded the instrument a lot, making it more sensitive, more capable. And we have software packages that are taking all of the data coming out of the telescope, doing all this filtering and trying to get this signal. So do stay tuned for this. And hopefully we will make this measurement very soon. All right, and that's my final slide. Thank you so much to you all for being here. Mentorship has been so important to me throughout my career, so a huge thank you to all of my mentors, Professor Greg Hallinan here at Caltech, as well as my PhD advisors, Professor Miguel Morales and Brenna Hazelton at University of Washington. Thank you to the whole OLWA Stage 3 team that I work with every day. And thank you to Cameron and the Caltech Stargazing Lecture Series for having me here. All right.
We can take some questions from the audience.
So you show the diagram of the spectrum and which parts of the spectrum are blocked by the atmosphere. And it's kind of counterintuitive, at least to me, that you would think that, there might be a threshold above or below which the atmosphere would block, but it's kind of scattershot, like it blocks really short waves, it blocks really long waves, lets all the visible light through, then randomly there are these spikes. What accounts for that, like in terms of what are the physical properties of the atmosphere or of the wavelengths that makes it so, especially in this region, in the middle, where some of them are fully blocked, some of them are partially blocked, et cetera?
Yeah, that's a great question. So the reason different things are blocking different wavelengths of light. So in the radio spectrum, which is my area of expertise, the very long wavelengths are blocked by the ionosphere. So this is, we have a lot of electrons swirling around in the upper atmosphere, and that's going to prevent long, exactly.
Picked up over a longer.
Exactly, right, which is really inconvenient from an RFI perspective also, that we see stuff over the horizon.
St. Louis and New York.
That's true.
Right. Yeah, with the more around the optical spectrum, this has to do with different elements that are in the atmosphere. So you get absorption from things like water vapor, from other elements. There's other folks in the audience who probably know more about all of these, lumps and bumps over here. But yeah, it's really if there's a molecule or an atom in the atmosphere that is going to absorb that light, then you don't get transmission through the atmosphere.
Other question?
How did you how did you determine the upper limit of the brightness of what you're trying to observe?
Right, yeah. So part of our work is we have to know very precisely the sensitivity of our instruments. So there's different ways that we do this, but we do a full propagation of, if we had a little bit of uncertainty in this step of our analysis, what does that mean for our final measurement? And so what that tells us when we go all the way through and we don't see anything is how bright something would have to be to show up in our measurement. And so if we get a null result, if we get no measurement, that tells us that any expectation for the signal that would produce something brighter than that can't be true. So for example, there's a prediction that if the universe was very, very cold when the first galaxies turned on and kind of after that, we'd get a very bright signal. And we know that that's not true. We know that the universe was warmer than that because we haven't seen it yet. Does that make sense? Okay.
Hello. I was wondering how many satellites are there out of the atmosphere and how many do you work with?
Satellites. So I work with ground-based experiments. So I don't work with satellite telescopes. I'd like to, and there's a lot of concepts for putting radio telescopes in space, either in the Earth's orbit or L2 or things like that, or in lunar orbit, which I'm really excited about.
And then the ones that with the picture with you in it, is that going to be the same thing that you guys want to put on the moon?
More or less, yeah. So there's a lot of different styles of antennas that we can use. They don't all have to look like this. But yeah, if we could just take this array and put it on the moon, I'd be stoked. If anyone wants to fund that.
I'm a little curious about why specifically you're choosing hydrogen, and also I noticed that the way you figure out how distant it is by the expansion of the wavelength. So my question is, how do you know that at that point you're getting an emission from a very distant hydrogen and not just a different element just with this wavelength?
Yeah, I think you answered your own question there. So the reason we want to use hydrogen and why the 21 centimeter line is so good is because it's really alone in the neighborhood of emission lines. And so there's not a lot else that produces line emission around 21 centimeters. If you see 21 centimeters, you can be pretty confident that it's hydrogen. What we do see as a contaminant is stuff that's not line emission. So there's a lot of things in space that produce, not at a specific wavelength, but kind of at all of the wavelengths. And so this is what we call synchrotron and free or Bremsstrahlung emission. And this is things that sort of glow because they're hot, like the fire in your fireplace mostly just makes light at all different wavelengths. And so that's what we really have to contend with. That's all of the, when I talk about, other and our own galaxies getting in the way, it's that not line emission stuff. It's convenient because we can filter it out based on the fact that it's not line emission. If it kind of shows up at all of the wavelengths, then we say it's not what we're looking for. If it shows up specifically at one wavelength, we know that it's hydrogen.
For hydrogen that is farther, like how do you still know it's hydrogen and not a different element?
Right. There's no other element that produces line emission longer than 21 centimeters. Yeah.
Got it. Thanks.
Yeah.
Oh, okay. One last question before we break.
Would a grid like that, you said on the moon would be great. Would there be advantages to having it on Mars? Would it be less obstructed?
Not necessarily. So what we really want is we want to put it someplace that doesn't have an atmosphere. So either the moon or Mars would work for that. And the moon is obviously a lot closer. The other thing that we need is if we're going to go all the way to the moon, we'd like to be on the far side of the moon. And that's just because then we have the entire moon blocking the human-made RFI that's on Earth. And so again, I don't see like an advantage to going to Mars or something for that. We just need to be on the far side of the moon. And that can either be on the surface of the moon or in lunar orbit when it passes over to the far side. Then we get that shielding of RFI.
All right. Let's thank our speaker again. Excellent job, Evie. So now we're going to have a brief intermission, and the telescopes are already set up. We'll have a panel Q&A in here for the next hour or so. One announcement that I forgot to make at the very beginning, there is a total lunar eclipse that takes place next week, next Thursday night. We are not doing an event here because it doesn't really start until like 10:30 or 11 at night. And man, I go to bed. I don't know. But the thing about a lunar eclipse is you don't really need any special, well, first of all, a lunar eclipse is when the Earth gets in between the sun and the moon. So it's blocking all the direct sunlight that normally is illuminating the moon and that we use to see the moon. And so when the Earth gets in the way, the only sunlight that makes it to the moon is kind of filtered around through our atmosphere along the edges of the Earth and makes it there. And when it filters through our atmosphere, it filters out all the blue light. That's why our skies are blue. And so the only light that reaches the moon during this period of totality is red. And so when you look up and see the moon for about an hour next Thursday night, Thursday, the 13th of March, around like 10:30, 11 at night, you'll see a red moon. And what's particularly interesting about this one is there were two crafts that landed on the moon in the last few days, and for the first time since the Surveyor missions in the 1960s, we're going to have a spacecraft on the moon watching a total lunar eclipse from the surface of the moon. So expect really cool pictures. It won't be live streamed or anything, but expect some really cool pictures probably on Friday, or at least in the Sunday papers, of images from the surface of the moon looking at the total lunar eclipse that takes place. But you will be able to witness it from here on Earth. And I encourage you to go out if you are still awake and up. Go outside, and if it's clear weather, you should be able to see a nice red, ruddy blood moon overhead. So it should be pretty cool. Okay, so as I said, we're going to set up the panel here. The telescopes are outside. You can go back and forth between the two, and otherwise, yeah, we'll get started in about 5 minutes. Okay, welcome back. Thanks for sticking around after the intermission. We're going to get started with our Q&A panel. So what we'll each do, we're each a member of the Physics and Astronomy department here at Caltech at various different career stages, and we will give a brief introduction to each of us as well as the science that we work on. And I'll write a little science topic under each of the names in case you forget or somebody comes in later. And then we'll answer questions, whatever questions you may have, whether it's about the evolution of the universe or SPHEREx's launch or the lunar eclipse that's happening next week or the asteroid that was going to hit us but now isn't going to hit us and or whatever you want. So I'm Cameron Hummels. I'm a research staff here in the department, and I'm the director of astrophysics outreach. My research is primarily focused on galaxies, galaxy evolution, the formation of galaxies like our own Milky Way, and using computer simulations to understand how that happens by running these big supercomputing simulations to model how it behaves over long timescales.
Hi, everybody. I'm Harsha. I'm a second-year astro grad student here at Caltech. So still figuring out stuff, but I mostly work also on cosmology, but instead of using early probes, I study the late time structure, which is galaxy clusters. So I talk about cluster cosmology, which is how we can understand about the different components of the universe from galaxy clusters, which are the most massive objects in the entire universe. They're collections, as the name suggests, they're clusters of galaxies, around 1,000 to a couple thousand of galaxies. And yeah, they're pretty fun objects to study about. So I can talk about components of galaxy clusters, about the different types of things that are in galaxy clusters, and how the turbulence within the medium of galaxy cluster help us understand physics of baryons and how they accrete to form these huge, massive objects.
Right, so hi everyone, I am Kenny Lau. I'm a postdoc at Caltech, and then my specialty is on the measurement of the cosmic microwave background, CMB. Well, I'm pretty happy that Ruby's talk already provide quite a lot of context. So that is CMB is basically the signal basically like coming from the Big Bang is the most distinct light that we can measure when the universe was still hot and compact. So by measuring those really early signals of the universe, we basically can know how the early condition of the universe and how it evolved after that. I'm a little bit on the experiment side. So the cosmic microwave background is basically signal falling in the microwave regime that is like about 1,000 times. The wavelength is about like 1,000 times smaller than the radio wave that Ruby's work on. So you can see in Ruby's talk, she built those really large antenna to try to measure those signals. While for our microwave signal, we build basically 1,000 times smaller antenna. This is the micro detector borrowed a lot from the semiconductor industry to build these micro detectors to measure the cosmic microwave background.
So you all kind of know what I work on. Once again, I'm a postdoc here at Caltech. And yeah, I do radio cosmology. So in addition to what I talked about, we are building a 2,000 dish array in Nevada that will be the biggest and I think the best radio telescope in the world. So ask me anything about that. It's called the DSA 2000.
Okay, so we open it to you guys. Do you have any questions? And we're live streaming on YouTube, so we'll occasionally take questions from the YouTube audience as well. But so yeah, YouTube audience, you can ask questions in the chat and I'll read them aloud.
Thanks. Yeah. So Ruby, earlier you said nothing emits close to hydrogen. Is helium the next closest, or what's the next closest element to hydrogen, and how close or far away from its wavelength is it?
That's a great question. I don't remember all of the spectral lines. So pretty close is hydrogen Lyman alpha emission. So hydrogen produces a lot of different emission lines. Those are quite a bit shorter wavelength than 21 centimeter. 21 centimeter is pretty unique because it's a really small energy splitting. It's So it produces such a long wavelength of light. Do you all know if what's like the next
So
lowest
I don't
frequency
know.
emission? Yeah.
I ran out to grab a microphone. Did you talk about the hyperfine?
No,
transition?
I
Okay.
didn't. Yeah. So this is the mechanism of 21 centimeter emission is neutral hydrogen in its ground state. If you do like, you can map out all of the energy levels of the hydrogen atom. This is a really small splitting in the ground state where it's because of the relative orientations of the spin of the proton and electron. So it's just the basically the magnetic interaction between those two. So that's why it's such a small energy splitting and such a long wavelength of light.
But I don't know in the far, like in the radio of other transitions. Like you said in your
Yeah.
talk, I don't know of other line emission. And the other thing that makes hydrogen so important, so welcome for this is it makes up the bulk of the normal matter that's out there. There is, helium, but I've never heard of a hyperfine transition in a helium atom that would yield some sort of
It gets
radio
pretty-
line.
It gets pretty like hydrogen is easy because it's one proton interacting with one electron. Once you start having more complex elements, there's much more discrete transitions that can happen, and that just becomes completely like the math of that becomes like out of control. Yeah, so we don't really bother measuring that.
Yeah. Yeah, sure.
The hydrogen that's really far away, how much does that wavelength change compared to like 21 centimeters?
Yeah, so we talk about this in terms of redshift, where redshift, so if something's at a redshift of 1, it's twice the wavelength. So it'd be 42 centimeters. And we're working with redshifts of about 20. So it's 21 times 21 centimeters.
Additional questions? Yeah. Thank you.
I feel like your current telescope is maybe in between 2 mountain ranges. And I was curious what considerations went into the new Nevada telescope. Are there other qualities of the area that make it good for your research? And if there's time, I thought the antennae design of your current telescope is so interesting. It's like little tents. Are there any new developments in antenna design, or has it remained kind of similar over the past decade?
Yeah, great questions. You're right, it's between 2 mountain ranges, and we love that. We love working in a valley, and that's because the mountains block RFI. So that helps keep the environment clean for doing radio astronomy. Now, that said, the Owens Valley is not the ideal place for radio astronomy because it's pretty populated. Nothing like the LA area, but there's a good number of population centers near there, and all of that's going to produce RFI. And so one of the main motivations for going to Nevada is just that we're building in Eastern Nevada. It's really remote. There's not a lot of RFI contamination. Also, the Owens Valley is just too small for the 2,000 dish array that we want to build. So we need a larger valley. And we chose Spring Valley, Nevada as a really great site. In terms of innovations in antenna design, yes, there's a lot of work building newer, better antennas. There's something called a Vivaldi feed that we're excited about at low frequencies that has a really even response across frequencies is something that we look for. The LWA antennas have been around for a long time, and actually there's a number of arrays across the country and even across the world using those exact same antennas. And they're surprisingly good for being as simple as they are and as inexpensive as they are. The reason they have that tent-shaped structure is because each pair of arms across from each other measures a different polarization of light. So if we get both of those, we can do full polarization reconstruction. And also the triangle shape helps us be, invariant to the frequency. So we can, again, measure a wide range of frequencies because of the triangle shape. So yes, but the LWA antennas are still good.
I'll just add that the Spring Valley site for the DSA 2000, this very large radio telescope that's starting construction soon, you can actually go there. You can't go to the site itself, but the valley, it's right next to Great Basin National Park, which is one of the most remote darkest sky national parks in the lower 48. So obviously sites like Death Valley or Sequoia are much darker than Los Angeles or San Francisco, but the farther you go from towns, the darker skies that you get because you have less and less light pollution. And radio frequency interference is essentially like the radio version of light pollution. And so where you're going to find dark skies to your eyes, you're also going to find these dark skies to radio frequency interference. So, and if you've never been to Great Basin National Park, it's really nice. It's really special. Other questions before we get back to you? A question in the back.
Yeah, I'm almost afraid to ask this because it's too basic. But Rudy, when you in your presentation early on, you showed the graphs that are linear and for the expanding universe. And I don't remember what the X and Y axes are. And it's super basic. But again, I'm not sure what you're measuring or how you're determining that the universe was expanding. And then why in its highest levels, and when that happened, there was a deviation. So I still can't, I know it's expanding, but I don't understand why from the basic level.
Yeah, absolutely. So the horizontal, I'm actually going to draw a picture.
I was going to draw. You want me to draw while you?
Yeah. Or you can explain. So the horizontal axis there is the distance to the galaxy. And what is the distance? Oh, yeah. So this is something I glossed over in the talk. You know the distance based on what we call a standard candle. So this is something where you know what the intrinsic luminosity is, and then based on the what you measure, you know how far away it is. And so these can be things like Cepheids, or they can be things like supernovae. With Cepheids, this is a type of variable star where the brightness varies in a very even way. And how fast that varies corresponds to how bright it is intrinsically. And so if you look at the variation, you can determine how bright it is intrinsically, compare that to how bright you see it, and know the distance. Does that make sense? Sort of, yeah. It's actually quite complicated. And we go to conferences and people are like arguing that folks have measured their distances wrong, and it gets really heated. On the vertical axis of that plot is the what we call the radial velocity. So that's the speed that these things are moving, and specifically the speed away from us, or it could be towards us, but the in the direction of our observation. And right. And so what we see is that almost all of those speeds are positive, meaning they're moving away from us, and they're moving faster away from us if they're more distant than if they're closer in. And the way that that is measured is through redshifting, typically. So we know kind of where the wavelengths of light are if they were nearby. We know that they've been stretched out. We know kind of how fast that expansion's happened, and so we know how distant they are. Or we know how fast they're moving, I should say. And so, yeah, then as we look at all of these galaxies around us, we see that all of the more distant ones are moving away from us. We could say there's something really special about Earth, that we're in the center of the universe and all of these things are moving away from us. And it's a lot more likely that the universe is expanding. Is that fair to say?
So yeah, the main thing of this is there are fancy ways with which you measure the velocity, which is basically how based on like their lines and their shifts based on Doppler effects. So for example, when you have an ambulance coming towards you, its pitch is higher than when it's going away from you, right? It's way more annoying when it's coming towards you. And that's basically how we measure these velocities of these galaxies as well. Things that are moving towards us have these like spectral lines that Ruby probably talked about, shifted towards us, versus when they're moving away from us, they're shifted farther away. So based on that, we get the velocities. And as Ruby said, we have ways to measure distances based on how certain stars pulsate or behave or radiate in a certain wavelength. So based on that, we basically can plot the speed versus the distance, and we figure out that things which are closer are moving slightly slower away from us, and things that are way far are moving farther away from us. And this is, again, as Ruby said, this is not that Earth is in a specific place in the Earth. This is for every single galaxy. So if you move to the galaxy on the opposite end of the universe is ill-defined. But if you move on a galaxy which is very, very, really far away, like in Star Wars, you can go there, and all the galaxies that a person there will see will also be moving far away from each other. So it's like, easy way to visualize this is like a raisin or a balloon model, where if you have a balloon and then you sort of like put dots on each other or on them and you blow it up, the dots themselves don't get bigger, but like the whole, like the space between the dots will expand. Or like a raisin in a bread or whatever model, where you have raisins and you bake the bread, so the bread expands and the distance between the raisins gets bigger. So it's basically everything is getting farther away from us because of the universe is expanding, and that's how people, and the deviation from the top is because the universe is accelerating, right? That's it. If you want to
I
add.
probably can quickly add a intuitive way to understand this. Usually used in popular science, probably not very rigorous in science, but I think it's intuitively you can imagine if you try to draw a grid on a balloon and then try to like inflate the balloon. Then you can really see like as the balloon expand, the grid will be like also expanding like gradually. And then that expansion, if you try to calculate that, the grid that further away from us will have a larger speed, like expanding as a balloon expanding. So this example is basically taking the balloon as a universe as a whole, telling you like when the universe is expanding, what will be happening for the object, which means the galaxy right here on the universe. So in that example, basically also can tell you why, like, if you observe in every single directions, all of the galaxy will be also like going away, because it's really like an expansion of the balloon itself, which means it's the universe itself. So all of the points that you observe around a particular observation point, they all going away. So.
Okay. There was a question online that I figured I'd ask of the group. So it was about radio antennae, and you've got the LWA, the shape of them is kind of unique and such, but can you just throw them down, your various different antennae kind of wherever they fall and still get a signal, or are they placed in specific locations that bring out, a better signal? Do they have to be placed in specific locations, or can you just scattershot throw them down on the ground at wherever random location and expect a result?
You get different measurements based on where you put them. It turns out scattershot's pretty good. We like them to be in, pretty random places. It turns out that, so this is a technique called radio interferometry. That's how we build these arrays of many antennas and have them all work together nicely to act like one big telescope. In interferometry, the close together antennas measure things that are big on the sky. So if you have two really closely spaced antennas, you're measuring things like the whole Milky Way or something like that. The more distant antennas measure things that are small on the sky. So you really get your resolution from the distant antennas. And we want both. We want to understand the sky on large scales as well as with good resolution. And so we try to have a good balance of those, having some close together as well as some more distant. The reason I say it's good to have them scattershot is because you want as many different measurements from the pairs of antennas as possible. So some arrays you'll see are in a grid pattern where all the separations are the same, and you're essentially measuring the same thing over and over and over again with all those different separations. What we prefer is to have lots of different separations. So every antenna, is making one measurement with each of the other antennas, and then each of the other antennas is making more measurements. So you get n squared measurements from the number of antennas squared. And ideally, those would all be different things so we can capture as much information about the sky as possible.
There's kind of a follow-up question related to that. And how do the radio telescopes, either the long wavelength array or the DSA 2000 that you were talking about, how do they compare with the one that's in China, which is, larger than the Arecibo that was in Puerto Rico. I guess the FAST telescope in China is the big single aperture, whatever, like 500 meters across or something like that. So how do the arrays of things that you're describing kind of compare with these single dish telescopes?
Yeah, there might be someone here who knows more about FAST. Talking about single dish antennas versus these arrays. These huge dishes are great at looking for very faint things. And so with the entire dish, you get a collecting area that can pick up really, really small amounts of light. That's not really the regime that we're working with when we build an array. So when we build an array, we're looking for imaging performance and the ability to resolve out small things. We're not really looking for faint things so much. So it's kind of a trade-off, right? Do you want to be able to measure very faint light, or do you want to be able to measure different scales on the sky and be able to reconstruct the sky to high fidelity? Does anyone else have anything to add to that?
No, that's
okay.
That's great. Let's see. Some more questions.
Can you talk a little bit about why the triangular shape of the antenna makes it frequency independent? Because from pictures I've seen, the previous radio telescopes, they're kind of like parabolic, like or pieces of parabola, many of them, right?
Sorry, pieces of what?
Pieces of parabolic shape.
Oh, yeah, right.
But so what makes the triangular shape so special?
Right. So the parabolic shape, are you talking about a dish in that sense? Right. So the antennas you see with the LWA are equivalent to the feed of a dish antenna. So I'll explain what that means. The dish is a reflector, and so it reflects all of the light like a big mirror into something that actually picks up that light in terms of measuring a voltage. That entire tent-shaped structure is what picks up the light. So if you wanted to build a dish for an LWA antenna, you would build a huge dish, then take that tent-shaped antenna and put it upside down on top of it. So we could do that. We've actually thought about doing that. The way that the LWA antennas are right now, we don't have a dish. We do have a reflector that's just on the ground. So it's flat, it's not parabolic. And that's actually made out of chicken wire. So it turns out at these long wavelengths, chicken wire is a perfect mirror. So we get away with using really inexpensive materials to make these things. I worked on another telescope that was all like PVC dishes. It's kind of fun. The reason the triangle shape is good for different frequencies is different parts of that triangle. You want something that's kind of scale invariant. So different parts of the triangle respond to different wavelengths of light. And so that full extent of the triangle is going to give you resonances with different wavelengths.
Yeah, that's great. Question in the back. Are you holding up your hand or? No, okay, you're not. Sorry. I didn't mean to embarrass you. I'll get to you in 1 second.
Thanks. For Kenny, I think. So the cosmic microwave background was emitted, less than 400,000 years after the beginning of time, essentially, and we can't see anything before that because it's too opaque. So that light has been traveling for nearly the entire length of time, and it should be really, really redshifted, right? But yet, you talked about how these wavelengths are still really short and much shorter than the long waves that Ruby's looking at. So what is the scale of redshifting for something that's been traveling 13.8 billion years? Like it shifted from what to what? Because it's obviously the scale of it must be relative to where it started. It must be a significant redshift, but yet it's still not very big, right? Mm-hmm. Can you explain that, like the numbers of that?
You're particularly talking about the redshift number for that. So, right.
Well, both what was emitted as well as what it started out as when it was emitted, and then what it redshifted to that we can see now.
So, the precise number is about like 1,100. So, which means like it is
Lyman alpha.
Z is 1100.
Oh, the redshift.
The redshift,
forgive me. I'm sorry.
Right. The redshift is like 1,100. Which means like when you, yes, right. That is like basically the moment of what we so-called the recombinations, which means say like you can imagine in the beginning of when up way after the Big Bang, the universe is really hot and compact, which means like there's a lot of charged particle, the plasma, wrapping around the CMB photon as well. They are tightly coupled together. So that means like the CMB photon cannot escape from that plasma. You just like no way to observe it. But after the universe expand, the temperature decrease, this plasma, for example, like the proton and electron, will combine together, become like one proton combine one electron, exactly the neutral hydrogen that we've been talking about. After that, it becomes like visible because there is no longer the ionized plasma surrounded by the photon. So at that moment, it's what we call the recombination. The photon can pass through this neutral hydrogen atom and can reach us. That moment, the redshift is exactly, right now, it's a very precise measurement, about like 1,100.
Just to give a more idea of what this actually means. So as he said, it emitted like redshift of 1100, which is a way we measure distances and time. But right now, the universe, if you look up pointed radio telescope, the CMB or the cosmic microwave background temperature is around 3 Kelvin, which is really, really low, right? When it was emitted, it was 3000 Kelvin. So it was a hot plasma gas. So 3000 Kelvin is something that you don't encounter on a daily basis. Like it was, if is it X-ray? It's not probably X-rays, right?
I think it's, he wants to know the wavelength of the emission.
Yeah, so it's
3,000. So it's like 1,000 angstroms.
Yeah,
like
it's 100 nanometer because it's right now it's, no, what we see now is, it's 1100 times. So it's right now it's, so right now it's 100 gigahertz. So if it's emitting, the CMB right now is in 100 gigahertz of frequency. Back then it was 1100 times more. So 100 gigahertz times 1100.
So in terms of the wavelength, it was about 100 nanometers, the wavelength, when it was emitted, and it is now redshifted roughly 1,000 times that. So instead of being 0.1 microns, it's about 0.1 millimeters. Yes, it's gone from the UV part of the spectrum when it was emitted to the radio, basically. It went through the optical. There was a time when it was in the optical. There was a time when it was in the infrared, and now it's all the way into the radio.
Can I add one?
Yeah, please. Sure.
Also, that's where most of the emission of the CMB is. It's one of these things that really makes all different wavelengths of light. So that's where the peak is, but we see it at all wavelengths, essentially.
Because it's a black body.
Yeah.
So, okay, sorry. Other questions? You had a question, right? No? Someone? I thought so. Oh, you have one. Perfect.
I think this one kind of goes off of this last question. But in the diagram in the presentation on the expansion of the universe, right after the cosmic microwave background, there's a period of the dark ages. What is it that stopped light from being emitted during that time? Why can't we see that time?
Yeah, absolutely. So, essentially there were no stars or galaxies. So there were no bright luminous objects. That's not to say that there was no light period, because you still have CMB light propagating through it, and you still have the 21 centimeter emission from the hydrogen gas that's throughout the universe. What you don't have are the really bright things, the stars and galaxies. And that's just because there was nothing dense enough. The universe was too uniform. So what you need to have a star is, a really dense clump of matter that allows for, nuclear fusion to glow. And it was just too uniform for that. So it's just kind of all the stuff was spread out too much.
But later on, gravity allows those clumps to get denser and denser and eventually form stars where it releases the energy of the binding energy of the protons and the atoms in their interior, and then they glow. Sure. Here.
Where do you know red light from? Is the material, kind of the temperature of that material existing, coming from whatever was there? Or is it, like you said, too uniform to detect?
Right. So the question is whether you'd have like black body emission from the gas itself. Yeah, I guess to some extent. Yeah. It wasn't terribly hot at that point. So nothing like pre-CMB.
Yes, I agree.
Yeah. I never really thought about that. So thank you for that question. Yeah.
Yeah, it's not totally dark. You just don't have these bright sources like we see when we look up in the sky and see stars and galaxies and everything like that.
I think it's just dark in the optical. That's the only regime it's dark at. It's like dark in the regime we can see, but it's pretty rich and not rich, but it emits an infrared radio, so on and so forth. Yeah.
You have a question in the back? Okay.
So long ago, the circumference of the universe, if I can call it that, was much smaller, and the peak frequency of the CMB would have been in visible light. How much illumination would that have provided for the night sky on a hypothetical planet back at that particular time since the Big Bang? What order of magnitude of light, visible light, would have permeated the night sky?
What's the surface brightness of the CMB at high redshift during the dark ages?
So
I don't know.
The number density, I don't have the numbers on the top of my head, but the number density of the CME photons right now is around 400 per centimeter cubed. The number density scales as redshift cubed, because the redshift is basically determining how fast the universe expands. Redshift is basically a number that is inversely related to how fast the universe expands. So back then, which was what redshift, what's the redshift for the dark ages? Dark ages 20, 30, 40, 50?
50, yeah.
50, okay. So if it's 50, then your universe would have been 50 times smaller than it is today. So that would, the volume basically of one, because everything is expanding, right? So the volume of one unit cell is 50 cubed times smaller than today. So the number density just scales as 50 times 50 cubed. So number density just scales as the volume cubed. So it's 400. It's 400 right now. The universe is bigger.
But in
smaller
turn,
back
I mean, but you're trying to ask, like, is it like a moonlit night or something? I'm trying to put this in the perspective of like some, numbers.
Yeah.
I don't think so.
No, definitely not. No, with that.
I don't know the answer.
It
That's a
wasn't.
hard-
Was it in the? It cannot have been in the optical by then.
It was I don't know about.
No.
I mean,
30 times radio is not optical.
no. I mean, it would have been very shortly after, because
It
it
would have-
started in the UV and it only had to expand by a factor of 5 in order to get into the optical. So,
Right.
and this is like a factor of 20 times later. So,
Right.
no, it'd be in the infrared by the time.
Yeah,
it's
it will
like
be
the
in
main
infrared in the
dark ages.
Yeah, so there's nothing optical in the dark ages. The CMB is in infrared. The gas is probably colder or not. But yeah, it would not, if you were a crab or something, whatever sees in the infrared, I have no idea what sees in the infrared. If you were one of the spy cameras, it would not be very bright.
Oh, it's just an interesting question.
Yeah, it looks pretty cool. Thank you for that question. Does anybody have?
Other questions that people may have? Yeah.
Jump out of my chest because I'm so nervous.
Oh, don't be nervous.
This is so elementary and you guys are way up here. So the first one, which I'm really embarrassed that I don't know, but do we actually know the size of the universe?
That is a great question and don't.
Okay, that's what I sort of thought, but I wasn't sure. Okay. And the second one was because, and my son thinks he can explain it to me, and he thinks you did it with the balloon, but you made a little comment about the Earth being the center of the universe, but we can tell it wasn't because the whole place is expanding. I didn't see where you were like, that's what we used to think, or that was a theory they had at, the beginning of scientific, and now we know it couldn't be because so I was confused on that. Okay. Yeah.
We'll elaborate. Go ahead.
I think I said that inelegantly. And first of all, I just want to say, like, these events exist so folks in the community who don't, spend every day upstairs, have an opportunity to come learn about what we do. So please, like, don't feel embarrassed about asking any question. This is for you, essentially. I think I explained that inelegantly, but essentially, imagining that we're looking at all of these galaxies, the close-in ones near us are moving away slowly, the more distant ones are moving away more quickly. What can we conclude based on that? And the natural conclusion is that the universe is expanding. And the reason for that is we have no reason to think we're anywhere special in the universe. And so in order to make sense of what we see and that there's this, distance velocity relationship with all of these galaxies around us, we'd like to think that it's the same anywhere we would go in the universe, because it just makes no sense that we're someplace special. And that's kind of what lends credence to the idea that the whole universe is expanding.
But the analogy that we kind of mentioned a few times, the one that really opens it up for me is the one, and I'll bring it back because I like blueberry muffins. So if you imagine that you're baking some blueberry muffins in the oven and you put in that blueberry muffin dough that's much more dense than it will be after it's done baking, and you put it in the oven and it starts to expand because of the yeast that's present. And so the dough itself expands. And from the perspective of any of those blueberries in that dough, all the other blueberries appear to be moving away from them. It doesn't matter which blueberry you choose the perspective of, all the other blueberries are moving away from you. And the ones that are farther from you are moving more quickly away from you because there's more dough in between you and them. And that dough is kind of just expanding linearly based on its location. And so it doesn't matter which blueberry you are, just like it doesn't matter which galaxy we're in, all the other galaxies look like they're moving away from us. Not because we're in the center or that other one is in the center or that one is in the center, but because space itself is expanding and causing everything to move away from each other. Sure. Yes, but that doesn't answer your question.
It does, but it forces another question, which again, I'm like, so you said that there's nothing special that should make us think, but Earth being so unique and holding human life and having water and all that it's made up, I don't see how you could say it's not something special, because from my understanding, the Earth is really special. I mean, there's nothing like it from what we can tell anywhere, right? At least yet.
That's right. And thus far, what we've detected in terms of the planets that we've found, it is unique in that perspective. But just because something is unique doesn't necessarily mean that it's going to be the center of the universe. Like, we might find a beautiful species that's like the perfect plant, and it might exist somewhere in Asia or somewhere in Africa. But does that mean that that place is the central location? Just because that exists there, that's like the central location in the entire Earth or in the entire solar system? No, it means it's a unique, interesting place that is important specifically for us and for the life that's here, but not necessarily that it has any significance in a cosmological, universal perspective. So. And your very first question, I kind of glossed over and I said, we don't know. So your very first question was, do we know what the size of the universe is? And that is an excellent question, because there's a couple of different ways of thinking about this. And one is yes and one is no. And the way I'll explain a little bit more is that because the universe, we believe, started at a certain time in the past, the Big Bang, per se, which is like 14-ish billion years ago. And because light travels at a fixed speed, it's not instantaneous. Even, we turn on the lights and it seems like the light reaches our eyes instantaneously, but it's just traveling very, very rapidly. But what that means is we can only see a certain distance away from us because there's only been sufficient time to allow the light to travel to us in that time period. And so we have something known as the observable universe, which is essentially how far away we can see that it's been roughly 14 billion years for that light to travel to us. There's some other factors, but essentially it's a sphere that's centered on us that goes 14 billion light years away from us. It goes farther because the universe is expanding, but we'll just, for simplicity's sake, say that. But we don't know what's on the other side of that edge. And every year that goes farther in time in the future, that sphere expands a little bit because we have longer to allow the light to travel to us from these more distant locations. But we don't know what's on the other side. So that's why I say, yes, we have a size, and that size is just our observable, but that's just determined by how long the universe has been around and for us to acquire information from a certain distance. But beyond that, I mean, the universe could be infinite. We just don't know. And there are various different models that propose that, it is infinite in its extent and it's expanding, but that's weird to think about, that it's expanding because it's infinite. So how could it expand further? But yeah, it's a mess.
Can work out that something like 95 billion light years across or something like that? So you factor in expansion.
When you factor in expansion, yes. Right.
But I've seen that number. So is that just one theory, or I thought the math gets you?
It's so measurement. Oh my God. According to our best measurements from a bunch of different sources, we currently think that the universe is flat. So that helps us a lot in determining the geometry. And okay, there are different things that the universe. There are three different shapes that the universe can have, depending on the total amount of matter in the universe. And this is all maths, but you don't need to get there. But if the universe is flat, it's just flat and infinite. It could also be spherically and curved, so it would be a sphere. In which case, it would be bound and it would be finite, sort of, because then it would start from a point, it would go up, and eventually it would collapse back in that point. So if the universe was a sphere, then the end of the universe would be in sort of a massive collapse back on itself. That's what math predicts. The third shape of the universe is what is a saddle, like a hyperbolic universe, and that is also infinite in nature. So its eventual fate of the universe at the end of the day keeps expanding. Again, it brings into the original part that Cameron said that, oh, if it's infinite, what is it expanding into? Blah blah blah. Infinities are hard, as hundreds of years of math has proved. But currently, from our measurements, we think that the universe is flat, which means we think it is infinite. Think being the current word, important word. But as Cameron said, all that we can see is our observable universe from where light reaches us. 42, but yeah, 40 billion light years. The radius of the observable universe.
Okay, sure.
Yeah. Yeah.
This and then this and then this. So, sorry, we'll get to all the people. Can you pass?
Yeah, we can do that. Here you go.
Okay, so in your blueberry muffin analogy, what is the dough of the universe? Is that what dark matter is kind of predicted to be, or?
It's space in between us and galaxies. That space itself is expanding. It's very slight. Like the distance between you and me right now is ever so slight that we can't really perceive it. But on very large scales, it's perceptible to see this velocity, the speed at which things are receding.
But how does the concept of space expand? Okay.
I don't know.
Well, I probably can try to use the balloon example to try to explain it once again. So you can really imagine, say for example, you have a balloon right here, and then you draw a spot representing us, and then another spot representing another galaxy. and you try to inflate the balloon, you can really see that distance, between the two spots, just like expanding, because like the balloon itself expanding. So you really can imagine that the balloon itself is like the space itself.
He's sort of asking what is the balloon?
Right,
No,
right.
Yeah, what is the balloon? What is the dough? And
Maybe to torture this analogy more, like the air that's being blown into the balloon is something we call dark energy. And once again, when we call things dark, it often means like
we don't know.
So yeah, it's again a big mystery why that exists.
And I should just mention, they're going to shut down the telescopes in the next 5 minutes. If you haven't had an opportunity to look through the telescopes outside and you want to, get moving, and hopefully you can catch. I'll message them and say, leave it open for another 5 minutes before they shut them down. You had a question.
Yeah, it totally led into where it went to, because I was going to ask, you mentioned dark matter earlier, but then the question of where is dark energy playing in all of this? And then when I thought about the expansion of the universe, it was simple, but then I also understand that Andromeda and the Milky Way are colliding. So if it's expanding, what's bringing the forces together, and is that dark energy?
Who wants to talk about gravity?
Yeah, right. So there's an interplay going on, right? Because you have expansion of the universe, this dark energy, but then you also have gravity. And so what you end up getting is this like push and pull where things are being pulled apart, but also collapsing. So if you get enough stuff in one spot, it'll get closer together, not farther apart. So there's really beautiful simulations of this happening where you see, the distribution of galaxies was relatively uniform across the universe at the beginning. And then as they're, on average moving apart, they're also collapsing down into this filamentary structure that we call the cosmic web. So any two galaxies, especially if they're close together, are likely getting even closer together. But on the whole, things are getting farther apart.
I was looking up a question that was asked of our online audience. There's a question here. Ruby mentioned she's looking at redshift of 20. Would that be approximately 100 million years after the Big Bang? And will she see the first galaxies in early formation or other early structure? I wasn't really quite clear on the simulation slide.
Yeah, so redshift of 20, I don't know exactly how many years it is after the Big Bang, but it's after the first galaxies have turned on, which is about 300 million years after the Big Bang. So it's really when those galaxies are starting to heat the surrounding gas in an
I
appreciable
know
way.
the highest redshift stuff that we're seeing with the James Webb Space Telescope is like redshift of 14 or 15, and that's at about where the universe is about 200 or so million years old. So I guess, yeah, redshift of 20 should be about 100 million years old.
100 million years, okay, yeah.
Oh yeah, questions in the back. Well, the online audience won't know what the question is if you don't speak into the microphone. What will we do?
Okay, here's your basic elementary question. What caused the Big Bang?
Big match. Yeah.
I'm trying to pass the microphone to someone else.
Yeah.
Yeah, well, this is excellent questions, but we really do not know. I guess this is also like one interesting part that why we are doing the science. I think what we are trying to understand right now is like the model, cosmological model predict that there is a beginning. What we call is a Big Bang. And then what we are doing, you can see the whole talk talking about cosmic history, is that we are trying to push our understanding closer to that moment. Right now, we actually have a pretty successful model to describe what happened a tiny fraction of a second after the Big Bang. So we are still trying to push a boundary to what really happened, closer and closer to Big Bang. But will we eventually understand what is why it causes whole origins? At least we do not know at this moment.
Yeah.
We are working really hard on this. So.
Yeah, we don't understand the cause of it. It's a difficult question. And as scientists, our our responses are governed by evidence for different things. And as such, answering that's like almost a deep philosophical question that we don't have a significant piece of evidence that points one way or another. So there are scientists, some notable scientists who've tried to enter into answering questions like this, that maybe there's a multiverse or there are multiple kind of bursts of big bangs setting off new universes within a larger fabric, within a larger structure. But largely it's speculation. There's not a lot of pieces of evidence pointing towards one or the other, because it's very difficult for us to understand something kind of from the outside and the motivating factors into that when we're kind of inside that structure. Sorry, I know that's not the answer you wanted to hear, but I don't think anyone has an answer for that question, or at least no credible answer.
And if you really want to break your brain, so the Big Bang is the start of space in the universe, but it's also the start of time. So you can't really ask the question of like what precipitated the Big Bang in a like a causal time kind of sense.
I know it's counterintuitive because, yeah, I know it's challenging. There was a question, but he left. There's questions. You already asked a question, right? Okay, I'll get back to you.
Okay. No, correct. I'll ask something a little bit more practical. So on one of your slides, you had kind of like the different layers of electromagnetic observations that we can make, and the base one was the CMB, and then the next one was the hydrogen something or other. And I was just gonna ask, what was the name of that again? And then also, what's the difference between those two, and what's their relationship? If that makes sense.
Is this the slide where it was like all of the layered things that we
Right.
see on top of each other?
Right.
Right. So the CMB is the earliest light we can see. So this is at a redshift of 1100. The hydrogen stuff that I'm looking for, we refer to, the cosmic dawn, or you might sometimes hear the epoch of reionization is another thing we're trying to measure. Those are happening quite a bit later in cosmic history. So it's more nearby. And it's, specifically looking at that hydrogen gas from around the time that galaxies started turning on.
Yeah. And so there were a lot of variations in the cosmic microwave background that you said were turning out to be really useful for modeling the universe. So I was wondering, how is that variation related to what we see in the hydrogen level?
Yeah, I'll let you talk about the variations in the CMB.
Right. I guess especially for the hydrogen part, that I would refer it particularly for the cosmic dawn or like the reionization process. So as you can imagine, because CMB is like the background light, when it passes through the cosmic dawn process, the reionization process, actually that will slightly alternate the intensity level of the CMB. Also, we try to create some polarization of the CMB. So actually, if you try to this is one of the CMB measurement can be useful to try to put a pretty weak constraint on the cosmic dawn that Ruby is studying. But I think what Ruby experiment is trying to more directly detect. You can see if you're using CMB to go as a background light to try to put a constraint on that, it's just because CMB is passing through it, so it's not the direct constraints. So while what Ruby is studying is trying to really detect those signals directly coming from the cosmic dawn regime, so that we try to make a much stronger constraint on what's happening in that evolution. So.
I can add a little bit. Yeah, I can also add. So in talking about the variations in the CMB also, one of the reasons I should say that we're so interested in the variations is that is talking about overdensities, more dense and less dense stuff at the time when the CMB was emitted. And that is what seeded stars and galaxies, because remember, going into the dark ages, we have this gas that's almost uniform, and then there's some regions that are more dense than others. And so we're seeing that imprinted on the cosmic microwave background. So that's really our baby universe seed coming from that. And so we want to understand how those overdensities propagated all the way through, because we're interested where galaxies came from, and also the details of how dense those things are and how they collapse under gravity tells us things about how fast the universe, this push-pull thing, how fast the universe is expanding, and what gravity is doing, and where gravity also tells us about dark matter is the main source of gravitational attraction. And so I would say that the fluctuations, the variations in the CMB are really similar to the variations that we're looking for in hydrogen, in that they're talking about, this clustering of matter throughout the universe. The hydrogen variations also depend a lot on the actual astrophysics going on with early galaxies, though. So there's more complicated stuff happening where it's talking about how fast certain regions are heating, how fast certain regions are ionizing because of those early galaxies. So it ends up telling you slightly different things that depend on, the masses and the dynamics of those early galaxies.
No, yeah. It was just basically what, she said. There was in the CMB, there are two types of like fluctuations. The first is called the primary fluctuations, which is what she was mentioning, which is due to when the CMB was emitted, these overdense regions, they were slightly more denser, which collapsed to form these huge, pretty galaxy clusters and like nodes in the cosmic web. And then the underdense regions, which collapse to just form voids, like giant regions of where there is not absolutely nothing, but very, very low density gas in the universe. So those are primary fluctuations in the CMB, and studying their sort of variations tells us about dark matter, dark energy. But there's also secondary fluctuations, which he mentioned, which is when the CMB passes through these huge things, like, because the CMB, as he said, is just background, right? It's like it's passing through things when it's coming to us. So when we see the CMB, it passes through galaxy clusters, it passes through galaxies, and so on and so forth. And that also changes the shape of the CMB. That also adds to the fluctuations in the CMB. And that's a secondary effect because of gas in the galaxy clusters and so on and so forth.
Additional questions? I'll get to you eventually. Okay. First, and then.
Hi, Cameron. Thank you all. I have a question about the mysterious, huge galaxies they found formed from the Webb telescope. And how does the radio waves, how does that information, how does your data with all the rest of the telescopes work, and what's been the impact of that redshift information on what you're doing with radio waves? And can you explain it to us, to everybody?
Yeah, absolutely. So the James Webb Space Telescope is finding really, really distant galaxies that are more distant than we thought possible. So this is telling us that galaxy formation got started sooner than we thought. Super interesting stuff. The reason we want the radio, so these are really complementary, right? We're both all looking for early galaxies. The reason we're not going to close up shop and say JWST, found early galaxies, we're good, is because we see different things in the radio than we see with something like JWST. And what those early galaxies are telling us, they're really extremely bright in order to be able to be detected. So we know that galaxies exist, but we can't really do population statistics. So we want to see like a whole bunch of these things to understand, are those really bright galaxies pretty characteristic of early populations of galaxies, or are they really an anomaly, that there's just a few of them and then there's tons of, smaller galaxies that we wouldn't be able to detect with JWST. The nice thing about radio and about our efforts to detect this 21 centimeter line is that we would really be seeing all of the hydrogen in aggregate. And not even from the galaxies themselves, but from all of the stuff between galaxies. So we would understand the universe on really large scales and not just towards these certain pinpricks of light. Does that make sense?
So the hydrogen that's between us and those galaxies, you can tell is there, but what are we learning from that we know there's galaxies there now? Besides that there's hydrogen in the space between now and the Big Bang, and also there's galaxies. Now we know there's these huge galaxies, which we didn't. I mean, the hydrogen that we see between now and the Big Bang, hasn't that already been perceived that there's been this data that's come in already?
Not at the distances.
Yeah, because the radio can reveal stuff from before the formation of those galaxies. It can reveal the presence of that gas at a whole continuum of different distances and ages of the universe on the way to those galaxies, but also beyond them, depending on the wavelength of the detector of the radio telescope that's able to detect it.
In an ideal world, the measurement I really want to make is JWST sees a galaxy with a light travel time of 13 billion years, and I put my radio telescope up there and see the hydrogen gas with light travel time of 13 billion years around that galaxy. And then I know everything that's going on. I know what the galaxy looks like. I know how it's interacting with the gas around it. And I can also understand whether that galaxy is pretty typical for its contemporaries or if it's pretty extreme. Does that make sense? Yeah, I mean, right. We've been interested in this first population of galaxies for a long time. And so I think a lot of folks are trying to study this in different ways, and in very complementary ways, where we're looking at different wavelengths, we're using different types of instruments to study it. And so the radio is just one. I think it's a compelling one for a lot of reasons. But yeah, we're certainly getting a lot of information from other wavelengths also.
But yeah, really the idea that I like to think of it as is that each wavelength of light that we can study, whether it's in the infrared using the James Webb Space Telescope or in the visible part of the spectrum from like the Hubble or from ground-based telescopes, or the radio like what Ruby was talking about, each of these is like a different octave on a piano. And so you can imagine, someone playing a beautiful piano piece where they're hitting many, many different octaves. But if you're only listening in one particular octave, you miss out on all the other ones. But really to hear the entire piece, the entire, cosmic opera or whatever, you have to hear across all these different octaves, which is really looking through many different types of telescopes, and they're informing each other. So the things you might see in the radio tell you something about the gas distribution, whereas the things that we see in the visible wavelengths tell us about, the stars themselves. But you wouldn't necessarily see the stars as easily using a radio telescope. And black holes are revealed in a different kind of portion of the wavelength spectrum. So you're really informed by having kind of this multi-instrument, multi-wavelength detection of these various different objects in the sky. There's a question here.
So you mentioned in your talk a little bit about the pollution of radio waves produced by like humans that we use in our everyday lives. I imagine that those signals are very, very strong compared to what you're looking for. Like, and the signals that you're looking for will almost look like noise compared to these signals. How big of a problem is that when you're trying to filter that out? Is it like purely a data analysis where that gets removed, or are there some kind of physical filters because radio waves we use are like so localized in specific frequencies? Okay, is there smart ways to do that, or is it purely a data analysis game?
Yes. So, right, we do filter them out, and it helps that they're in narrow frequency bands. So if something shows up, right spanning the FM band, we're like, all right, that is not astronomical. That is contamination. They also are time variant, so we use that to filter them out. And they're also localized in certain places on the sky. So we use all of those things to filter them out. What we're worried about is there's always going to be some in the data, right, that's below the noise. And so we can't filter it out effectively. And so that's what motivates us to build these telescopes in really remote areas. And I will say this problem is only getting worse with the proliferation of satellites. And so we get, and that absolutely kills us, because it used to be that if you went to a sufficiently remote place, you could kind of avoid all of the human-made RFI, but we see satellites from everywhere. So, yeah.
Are there specific times where it will be more favorable to watch because there's less radio traffic going on?
Specific times. I mean, with things like the Starlink constellations and other satellite constellations, there's almost always one visible above the horizon for our telescopes. So we can't really avoid it. We are working with Starlink to try to get them to, beam their signals. Like, please don't beam them right at our telescopes. And they're pretty accommodating to that. But yeah, it is a problem that will, continue getting worse for radio astronomy.
And really that's by design, right? Because Starlink is trying to provide internet to everyone regardless of location. So you're going to have these satellites overhead in order to get that.
So this was a follow-up to some things you guys said earlier. So at the Big Bang, the light was not in the visible spectrum. That was the dark ages. So if like a human magically teleported back to that time, like what would we see? Could we see anything? Yeah, I'm just hypothetically.
Do you mean just after the Big Bang or in the Dark Ages?
I guess the Dark Ages, but how long after was the Dark Ages?
Very long.
Like
Yeah, so at the Big Bang, I mean, you're at like a human transporting is like your atoms would be ripped apart from your body. Like
it's bad. It's bad.
It's really bad. It's like imagine really hot searing gas and you would just vaporize in a second. So that would not be fun. In the Dark Ages, you'll probably be really cold. You can't see. There's no optical light, so you won't be able to see anything. It's just be dark and cold, I guess.
I probably have a precise number. So the dark age basically is like the recombination, which is like a redshift of the CMB emissions that is like about 400,000 years after the Big Bang to the reionization, which is like 10 billion years after the Big Bang, I think. So that period is probably about like 10 billion years. So I don't remember exactly. Yeah, they're probably right.
It'd be a couple billion years between CMB and reality.
Yep.
Yeah, it would just be really dark and really cold.
Yep. Right.
Like space right now.
Maybe like a billion. You've got galaxies that are starting up in 100 million years after the Big Bang, and then they're starting to put out all this radiation, and we can see some of them, but they're in period reionization. They haven't fully reionized their universe at that point. That doesn't happen until like redshifted states.
And then the other question was, you guys mentioned that there was certain light that we could visibly see because it was so far redshifted. It came into the visible spectrum, so like we could see gamma rays because they were moving so fast away from us that they were redshifted into our spectrum. Is that correct?
Yeah, basically when redshift, what it does is like it moves things on the other side of the spectrum. So it keeps like gamma rays get transported to some other side. Like maybe they move into the optical and then, for example, UV would move into the infrared and so on and so forth. So yes, when the CMB was emitted, there was a period of time where it was in the optical regime. Yes.
Is there some of that's happening now? Like if we looked out into the universe, is there some like gamma rays we could see? Like, is it in some part of the sky? Like, or what?
There are actually.
Yeah.
There are, not optical, but there are studies of these really intense gamma rays when they interact with CMB photons or like cosmic rays, which are really, really energetic particles. When they interact with CMB photons, they can produce UV X-rays, UV rays, and other things. So not not optical, but there are cases of it sort of being not redshifted, but interacting with other things, and then ending up in the UV or the X-ray
Closer.
or the optical. Yeah, closer.
Okay, we'll take one. Oh, goodness. Oh, she hasn't asked a question yet, but you guys have asked questions, so you'll be our last question. You guys can ask them afterwards and we'll stick around.
Thank you very much. My question is, so in your slide, there was a slide that you overlapped many layers, and the layers of hydrogen radio wave was after the layer of CMB. So that means the signal we get from that will tell us about the early universe processes after the Big Bang, right? And so so we use radio astronomy to study this period. And also we know that tomorrow there will be the launch of SPHEREx. And the goal is also to study the early process of universe. So how do you think it can like support your study, or will it be an overlapped? Can you give me some idea of how it will support the study?
So SPHEREx, it's a really fun mission. So what it's gonna do is it's gonna survey the entire sky in the near infrared. So that's optical, the infrared regime, which is closer to the optical regime. And the point of it is the main science goal of SPHEREx is to constrain the very early universe, as you said, but we're not making direct measurements of that. So the way we're measuring that is basically, as she said, there was this period, very, very small, like fraction of a second after the Big Bang, where there was this period called inflation. And that sort of seeded the perturbations in our universe for like these overdense region and these underdense regions. So it started this sort of like density differences, which then propagated into the CMB. So from the cosmic microwave background, as we just talked about, we see differences in the overdense regions and the underdense regions. And that today form galaxies and galaxy clusters and like underdense regions of voids. So what SPHEREx is doing is trying to connect today's universe by surveying all the galaxies that it can see in the near infrared, map their positions on the sky, and based on these positions, look at the clustering to see, oh, this is an underdense region, this is an overdense region, and do some math to sort of like run back the clock to figure out what the physics was like, which seeded these differences in the perturbation. So we're not directly making, like these guys are directly making measurements of the hydrogen gas at a specific redshift. We're not doing that. We're making measurements of how galaxies look like today, and then running back the clock and seeing what that implies for the very, very, very early fractions of the second after Big Bang.
Thank you. And do you think that we can implement radio astronomy to the space telescope, or is enough to study on Earth's surface?
Yeah, right. I think there's a lot we can do from space, and it's also not just a proposal for the future. We're already doing radio astronomy from space. So very soon will be the launch of a mission called Sunrise, which is a constellation of little satellites where every satellite will work like a radio antenna. And so we get a full array of them. And that is looking at the sun. So it's going to be mapping out the sun. But yeah, I think radio astronomy from space will happen. It's really exciting. And there's a lot we can do from space that we can't do on Earth. We definitely haven't exhausted what we can do from Earth, but I think we should, yeah, do as much from everywhere as possible.
Thank you. Thank you for your presentation also.
Okay, that brings us to the hour. Thank you guys for all sticking around. And please, let's thank our speaker and our panel. Great work, guys. We'll be back in a month on April 4th. April 4th, I think, is the Friday. and our Astronomy on Tap is 2 weeks from this Monday on March 24th. Thank you. Dates are not my strong suit right now. And as mentioned before, there's this lunar eclipse that's happening next Thursday the 13th at about 10:30 at night. So go out and look at the red moon during that, and should be kind of cool to see. Thanks everybody. We'll see you guys next month.